Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. So today we are going to continue on MapReduce, and then we'll look into a newer system called Spark that takes it to the next level. But I think there's no better way to start than to ask you a few questions. Check that you've been following. So here is the first question. This is text documents and relative to XML, of course. So it's clearly that we would like to parse this as XML. And the question is whether this document is well-formed only, valid only, well-formed and valid, or neither of those, right? Is it well-formed and not valid, valid and not well-formed, valid and well-formed, neither valid nor well-formed? This is the document. The answers are coming in. Let me start looking. There is a majority. The majority is not always right, of course, but maybe it is. We still have answers coming in. Okay, now it's stabilizing. So let me show you the answer. It is indeed well-formed. So it is well-formed. Well-formed means that if you try to parse it, it will succeed. And after you have parsed it, because it succeeds and because it is well-formed, that will result in a memory, in an in-memory representation in the form of a tree, right? With the element nodes, attribute nodes, and so on, because we can parse it. Can anybody tell me why you didn't say that it's valid? Yes? Exactly, we need a schema for that. I didn't give you any schema, so you cannot make any statement on validity. And validity depends on the schema. For a schema, it might be valid. For some other schema, it might not be valid. So this is why I can only say that it's well-formed, right? So again, to summarize, because this is very important, well-formedness has to do with parsing the text, because this is just text, it's a sequence of characters. If it's well-formed, you can parse it into an in-memory representation based on trees with pointers in memory, and then you have all the properties of each node that are nicely populated. The other way is called serializing. You have the in-memory representation, and you serialize it back to something like this, that is the output, right? Why do we need this? It's because in between the parsing and the serializing, there will be the querying, right? The goal of putting in into an in-memory representation is that you will want to navigate, to query, to select, to project, to group, and so on, maybe on millions of documents. And at the end, you will produce some results, and then you serialize them back to XML like this. The same goes for JSON. You can parse JSON into an in-memory representation, then you can query it and then serialize it back. You could even have an input in the form of XML and an output in the form of JSON, right? You could even have Parquet as input or as output. It's just a binary format, but either way, you always get this in-memory representation that you work with, right? And so when you throw in validation into the mix, what happens is that when you validate millions of documents, the in-memory representation gets enhanced, right? So the in-memory representation will now have very precise data types because you check that they all, the lexical values all fit with the type. And then you can optimize the memory by using actual ints, actual dates, and so on, all in memory, and then process them. And if you have millions of documents that are valid against the same schema, and that schema has a few constraints that I told you, such that in JSON, only closed object types, and the types are all instantiable and so on, then you even have the luxury that you can put a data frame in memory, meaning that it is some super compressed, compact representation of the whole thing For those who know what it means, it's even a colon store in the sense that, not in the sense of HBase, in the sense that the values that corresponds to the same fields are all stored together. So it's highly efficient. But from the point of view of the user, this is all physical details, because from the point of view of the user, you're just manipulating XML and JSON trees, right? Do we have questions?
Yes, on Zoom. So would saying it is not valid also be wrong? It's just not decidable without a schema.
Exactly, it's undecided, if you want to call it that way. It's undecided because I did not tell you what schema it is, so you cannot make any statement on whether it's valid or not. Okay. I have another question for you. What is this P1 DT7H2M3S? Is it a UTF-8-based encoding of a protocol buffer? Protocol buffer is one of the ways that you can serialize it to a binary format. Is this a string in the lexical space of datetime duration, an XML schema type, and it's also a JSON and JSONic type because they are the same list? Is it an instance of a BSON instance that's MongoDB that we'll see in a few weeks in base 64, which is a binary encoding for JSON? Or is it the name of a new Star Wars robot? ETH, wonderful. Let me show you your answers. So yes, it is a string in the lexical space of datetime duration. What kind of duration is this? Can anybody tell me what's the duration here? Yes? Exactly, 1 day, 7 hours, 2 minutes, and 3 seconds. And this is a standard. It's a W3C standard. It's the same standardization body as HTTP, HTML, and so on. So this is good to follow if you're looking for a syntax for durations. Okay, and I have a third and last question for you, which is right here. You've just submitted a typical MapReduce job onto a large 1,000-node cluster. What do you do? When I say typical, I mean the sort of job you normally submit to a 1,000-node cluster, right? Not some outlier. So a typical job. So it's done before you ask. You go check the results. You go for a cup of coffee. It will be there when you're back. You switch to something else, and we'll check again in a few hours or tomorrow. Or you hide from the CFA. Multiple answers possible, of course. There a question? Yes, go ahead. Yes, it fully utilizes. This is what I mean with typical, right? So if you have 1,000, basically you need to submit a job that justifies that you build that cluster, basically. All right. So what do you say? All right. We have 12 people with industry experience here. So cup of coffee, says the majority. Well, the answer I expected was the third one. So the typical thing that happens when you use such a large cluster is that it's going to take several hours, maybe even the entire night, maybe even longer than that. So this is typical. You might also have job that runs faster than that, but really you have to imagine when you have 1,000 machines, all the time that it takes just to set up everything, trigger and bootstrap the whole job, wait until all the mappers, the mapping phase is completed. And you saw with the Pokemons, the time it took, and it was just for 100 Pokemons and 8 people, right? So Then there is the shuffling that's going to take forever, and then there is the reducing and writing back. So this is just really a matter of several hours. Of course, there's always outliers, right? You might have jobs that are faster than that. As you cleverly asked, you could have also jobs that use less of the cluster. But typically, if you booked a cluster like that, you probably want to execute a very large job. And the sort of jobs that you have, to give you a very simple example, is to index the web. If you want to index the entire web, typically you can do it with MapReduce, right? It's going to be gigantic quantities of data, petabytes, exabytes. And typically, I don't know if it has changed, probably these things evolve, but last time I checked, it takes 48 hours to refresh the web. So you see that kind of duration to be done. All right, but of course, it's only one of the many things you can do with MapReduce. You can also do matrix multiplication and so on. So there's plenty of things you can do.
There's a question
Yes?
on Zoom, but it depends on how big the data set we are mapping, reducing or not, question mark.
Yes, exactly. It depends on the data set. Yeah.
Using 1,000 node cluster for something relatively small, I would hide from the CFO.
Yes, absolutely. And especially if you forget to delete the cluster, because this is a common mistake. Who has already forgotten to delete a cluster? We have a few of you, right? You probably learned a lesson from your life. So for your life. So what happens, it also happened in former classes where we're using AWS or Azure and so on. On a class of hundreds of students, there always is a few students who will forget to delete. Fortunately, we go and beg Amazon or Azure to cancel the bill, saying we're academia, you know, and so on. And usually they're kind with us, so it doesn't have consequences. But when you're in a company, you really need to pay attention to these things, right? So do not forget to switch off the machines that you are not using. In fact, for some companies, you might even have some sysadmins that maintain a permanently running cluster of machines, sometimes even in the own premises of the company. And then it's all paid for, right? But then it's shared across the entire company. Do we have another question on
the only moment we call MapReduce is to read data, right?
To read
data.
To also write data. You transform data typically. So you have an input, you transform it, and then you get an output. And you can even chain multiple jobs, because you do have real world problems that a single MapReduce job doesn't suffice to solve, right? So sometimes you have 2, 3, 10, 100 jobs, you just chain them, and every new job takes the output of the previous job as its input, right? So this is a typical, I might have time to show you PageRank, how you can actually compute the PageRank for web pages. And this is done with matrix multiplication, and this requires several rounds of MapReduce, typically.
We have very active Zoom chat today.
Oh, that's good.
What happens if one or more of the nodes crashes during MapReduce?
Oh, that's a good question. Let me also answer this. So if some nodes crash, so the answer is it depends. It depends when you crash. Let me start with the ones that are easy. Imagine that you crash during the map phase. One of the mapping slots crashes. What it means is that some of the tasks will be delayed, because what happens is that the other slots, they continue to run normally. They continue to query the data and apply the map function. And what happens is that the central, so the job tracker, is going to reassign the tasks that failed to somebody else. They're going to find another node, and they are going to assign to this other node taking care of the mapping, right? So this is a case where there's not too much consequences, and you can actually recover from that. But then you can also have cases where you lose data, meaning that you're done with the mapping tasks, and you might already have been starting to shuffle. And then you realize that some of the data is completely lost. In these cases, you also need to recompute them. And sometimes if you fail during the reduce phase, that one of the reduce slot fails, or maybe some data is lost, then you might have to retrigger the entire mapping phase all over again. because you need to reconstruct the intermediate key values in that case. And if you lose the intermediate key values because the node completely crashes, the node that downloaded them completely crashes, and you also deleted the copies from the mappers, then the worst case is you need to redo it all over again, right? And something also that can happen, who has ever been an intern in a big company running jobs on the cluster, who already got preempted by running the job? Some of you, right? And typically this happens when the full-time engineers, they have priority over the interns. There's many other rules, but that's an example. And in that case, that might stop your entire job in order to give the resources to somebody with higher priority. Then you just need to try again, right? It can also fail for different reasons. It can also fail not because MapReduce fails, but because you made a mistake in your code, in the map function, in the reduce function, or maybe in the input data, that it was not clean and there was a missing field somewhere that you assumed would be there, and then it crashes because it's not found. And then if it was for the entire night, you just need to do it again and then run it the night after that. Right. So this is a completely different experience than when you program in front of your laptop and you immediately see if it works or not. Here, you might have to wait for 24 hours until you see whether you fix the bug or not, right? And you can imagine how cumbersome it is over multiple nights. It's actually not new because the experience of our predecessors who are working on the very early computers, I don't know, in the 60s, 70s, maybe not, but let's say 60s, 50s. It was a completely different story because then you didn't have laptops or desktop computers in your office. You had a supercomputer. For example, at ETH, there were some. One of them is actually in the CAB building in the basement. You can still see it. It's a Cray computer, a Cray supercomputer, I think. And typically, what happened is that the students or the PhD students had to prepare their cards, punching holes in them, and then they would bring their punched cards to the room where they would take the jobs, and then they would batch the execution. So take all of these and execute them, and then you come back on the following day and see the results. And here too, they had to repeat and repeat and repeat because sometimes it would just fail, and you have to think about it and figure it out, and again wait for 1 or several days. So this is a whole different experience, and you really have to use your creativity and mind to make it work. Of course, there's also tricks that allow you to take some shortcuts. All right, some other questions? Yes?
Why don't the processes store the intermediate results in HDFS again, so they don't have to?
Oh, you can. You could also. So HDFS, I don't know. But typically, if you have enough space, then you don't throw it away. So basically, if you do have the disk space, you can start reducing. And after you transmitted the key value pairs to the reduce slots, you can keep a copy if you can. Of these, and then that removes the problem that you need to rerun it all over again. But it's really a matter of resources. Sometimes you don't have the space, or maybe the intermediate data is so large that you don't have the luxury of being able to keep it, right? Then HDFS, I don't know if that can be activated in some way that you would spill the intermediate data to HDFS. At least I don't know if you could ask MapReduce to do it for you, but what you could do instead is try once the job, if you have difficulties and it keeps crashing, you can rewrite your code with an identity function for the reducer and try to spill it yourself to HDFS, right? That would be the final output of the MapReduce job, but you just replace the reduce part with the identity function, right? It's kind of this debug, like this system out println way of seeing what's going on, right? Does it answer your question? Yeah. Anybody else? Any other questions? Yes?
You mentioned a few times the reduce space with the identity function.
Mm-hmm.
In this case, does MapReduce actually execute the reduce space, or does it just skip it?
It will still execute the reduce phase, but this is basically what I mean with the identity function is that it's your code that is the identity function, right? So it will still execute it, but of course, calling the function will be super fast because you just spill the intermediate key value pairs as the output key value pairs. I don't know if there is some way to tell MapReduce on a higher level that this is the identity function. That's actually something we could check. It might be that there is a parameter that informs MapReduce to optimize it even more, right? But as far as I know, the way to do it is just to write your reducer class as the identity function. I think Martin might actually be checking right now. Yeah. All right. Did it answer your question? Yeah. So, okay. Yes. It looks the same because you still want to group together the keys that belong together. And this is why I was asking actually whether there could be a parameter that informs that it's the identity function, because you're absolutely right. If you now think as an engineer implementing MapReduce, if you have the information that it's the identity function and that there will be no grouping, then you're correct that the shuffling is unnecessary, right? And the idea is that there is no limit to the optimizations you can do, basically. The sky is the limit. It's also something you will never be completely done about. There will always be cases that you did not optimize. And the typical thing is that when you have a product in a company that you offer to your customers, let's say a data-independent database system, you look at what the customers are doing, and you're going to try to optimize the common things that your customers are doing, and what they are not doing, then you won't try to optimize, right? And you're just constantly improving and improving. And this is the reason why all the database systems, they keep releasing new versions, right? Oracle, IBM, Microsoft SQL Server, PostgreSQL, because they keep improving things. They keep trying to make it better. MongoDB is a very good example. Now they are more stable, but a few years ago, at every release, there would be new optimizations. Like something that used to be slow on the previous version suddenly would become faster in the new version. You don't change anything to your code. It's just that it's able to detect more optimizations, right? And MapReduce, it might be that they also came up with some optimizations and way to skip some parts that wouldn't be needed. The important thing is that you really think like an engineer and think about these things from a physical level and figure it out. Because even if they didn't do it, it doesn't mean you could not do it, right? You could absolutely imagine doing things like that, right? Okay, should we continue? Yeah, and on Zoom, no activity? Okay, so I'll just project the slides again. All right, so this is really something I want to make sure I answer all your questions, that everything is clear, because there's a lot of pieces of the puzzle and there's a lot of moving parts, and it's good to build a mental picture of this. So as a reminder of what we've seen until now, from a logical perspective, this is what MapReduce is about. We have some input that might be stored on HDFS, on S3, on any storage medium you want. Then you have a map phase that maps in parallel the key value pairs of the inputs to the intermediate data. This one remains in the memory of the machines or can be spilled to the local drives if it doesn't fit in memory, but it basically is local to the machines. And then you have this big shuffling phase, the goal of which is to group together the key values that have the same key, make sure that they arrive on the same machine. And then you have the reduce part that kicks in. And finally, at the end, also in parallel, you're going to output back to HDFS or S3 and so on. And as a rule of thumb, you output one file for each reduce task. Right? So that's the idea. So the output, the typical output of a MapReduce job will be a directory with, I don't know, 1,000 files. That's a typical output. Okay, and that's the reason why, since I told you that the output of a MapReduce job can also be used as the input to the next job, MapReduce is able to read from a single large file, but it's also able to read from many files. So you can give a directory to MapReduce as the input, and it will automatically take every block of every file as a task. Okay, so this is the idea. Then this is the more details on the processing. The idea that you start with the key value pairs, you apply the map function to obtain intermediate key value pairs. Then logically, right, you sort everything and then separate by key. So all the key values with the same key are now together. And then you apply the reduce function to each group of intermediate key value pairs with the same key, and you obtain these right here, the output key values. And again, the map function and the reduce function, they can all output for each call 0, 1, or more key values. This is fully generic. It depends on the code that you're going to write. You have full control of this. But the very common case is that the reduce function really aggregates the values for the key, keeps the same key, and puts the aggregate in there. That's, I would say, in many, many cases, this is what you actually be doing. And in that case, you can even optimize with a combine function in the case that you aggregate with a sum or min or max, because in that case, you can compress the intermediate data very early by already pre-computing partial min, max, or sums in the system, like we did with the Pokemon. Okay, then I told you about the architecture, which is the same pattern with the centralized system with the coordinator node and the worker nodes, just like HDFS, just like HBase. So it just means that you need to learn new names. They're all collocated, meaning that the name node is collocated with the job tracker. The data node is collocated with the task tracker, which you can see in the lecture hall. The idea is that since the data nodes are collocated with the task trackers, you bring the query to the data. You really call the map function with the same CPU on the same machine that the blocks are in, right? So you try to avoid shipping it over the network, at least during the map phase, right? You only ship over the network in the reduce phase. Okay, so that's called bring the query to the data. Then this is the combine optimization. Like during the mapping phase, you can reduce the size of the intermediate data by calling the combine function. This is typically done arbitrarily. You have no guarantee of that. It might be that it's not even used at all, but typically it's at any time while it's in memory or when you flush, when you compact. So all of these are opportunities to call the combine function and have a smaller size. And this is really for anybody who works with big data scales, it's an obsession, this thing. You really want to very early compress, have as little bits as possible everywhere, because less bits means you read faster, you transfer faster, and so on. So I'll talk about that again, but you really want to optimize by having as small quantities of data as possible. Okay. All right. Then that's the Java code. I think we stopped there last time. That typically it looks like this, that you configure a job, then you implement your own class. Typically you call it mapper, reducer, and so on. And then you inform MapReduce, this is my map function, this is my reduce function, this is my combine function, optionally. In that case, we reuse the same combine function as the reduce function, the same implementation, probably because it was associative and commutative. You'd say what your input path is, which can be a file or a directory. On HDFS, on S3, you set the output path, and then you wait until it completes. Do we have a question?
How does MapReduce decide whether to use the combine function?
It does whatever it wants. But basically, the idea is that MapReduce trusts you. That's the contract. It's designed by contract, right? When you program. So the contract that you have with MapReduce is that you must supply a combine function so that it does not change the correctness of the results, no matter how often you call it. 0 times, once, twice, 10 times, on some of the data, on all of the data. You really have to make sure as the user that you respect that contract. And then MapReduce does whatever it wants. And then typically what MapReduce, the sort of heuristics that you can have is that maybe at some point the memory becomes full. So instead of flushing, it's just going to run the combine function throughout the memory to compress back to something smaller in memory. Maybe it's going to do that end flush. Maybe it's going to see when it combines or compacts several files to a single one, it will see yet another opportunity to see the combine function. These are all things you can do, but again, at least that MapReduce can do, but it's completely arbitrary and it might even change at every implementation, every new release of MapReduce. you might see a better behavior every time. So as a user, you cannot make any assumptions on what MapReduce is going to do. Right? You just need to promise MapReduce that the combined function is such that no matter how it's called, the results are correct. Okay? Did it answer your question? Okay. Awesome. Okay. So now I would like to conclude this lecture to take the time to go through this whole thing in a way that is even more fine-grained on the physical level. This will also be useful for Spark because this is exactly the same way for Apache Spark that we will see a bit later. The one message that I want to give you is try to not use the terminology MapReducer. Please don't do that. You will see it in many books, in many textbooks, in many YouTube videos, in many web pages, blogs, and so on. A lot of people say mapper and reducer. The problem of using the words mapper and reducer is that it's ambiguous. You don't know what you actually mean. What is a mapper? Is it the function? Is it the CPU that actually calls the function? Is it the task? You basically don't know. It depends on the context. So what I would like you to do also as a mental exercise and as a habit that you keep for the future, I would like you to say instead map task, map function, map slot, map phase, reduce task, reduce function, reduce slot, reduce phase, combine function, and so on and so on. Try to take the habit of doing that, and then you will see that will bring you a clarity of mind, because by making this distinction, you understand what's actually going on behind the scenes. So I will do this in the next few slides, but first with an analogy, in particular to really explain the subtle relationship between a split and a task, because I kind of said it's kind of the same thing, but semantically it's not exactly the same thing, even though there is a correspondence. So let's say that our friends here went to for a vacation and they want to send some postcards, and they have 50 postcards to send. Of course, they visited the big data lecture. They know about MapReduce, and they decide to organize the postcards in this way. The first thing they do is they split the postcards into 5 batches, 5 splits. We call them splits. Postcards 1 to 10 are in the first split, so maybe they pile them up on the table. Then they're in a second pile, a second heap, there is postcards 11 to 20, and so on and so on. So now you have these 5 heaps of postcards, which gives you 5 splits. They also realize that they can organize themselves in parallelization with 3 levels of parallelization, right? So we have 3 groups, and they will process these batches of these splits of postcards, these batches in parallel. So the splits are the actual postcards, right? I have 10 postcards, that's the first split, 10 postcards, that's the second split, and so on. Not to be confused with the task. The task is a to-do. Task number 1 is a to-do that you have to write on the postcards 1 to 10, whatever you want to say to your friends. That's the task. The split are the 10 postcards. The task is the homework, like what you have to do with these 10 postcards. And we organize the tasks here in a way that every split corresponds to a task, right? So the task for every task is to basically process 1 split. Okay, so far so good? The difference between split and tasks, who gets it? Okay, yeah, I'll go to the question. All right, go ahead. Yes, exactly. Yeah. There are indeed multiple reduce tasks, but a reduce task is not the same thing as the call of the reduce function. You might have multiple calls of the reduce function in a reduce task, but do not worry because I have slides. I prepared an animation and plenty of slides, and it will become very, very clear. I just wanted to do the postcard analogy before, but you will understand. When you see the slides and how I show you in detail, I hope it will be crystal clear, right? Okay. Okay, so now the splits, the tasks. And now they start. So they imagine them sitting around the table with the 5 piles in the middle of the table, and they each group here takes 1 pile. The last 2 tasks, for the moment, they still are at the center of the table. They haven't started with them yet, right? So it's going to be done later. So they start in parallel writing for these 3 piles of postcards, their vacation words. Now, it seems that with the extra help that Alice in the middle got, she's already done. What she does, because she's already done with task 2 and the others are not done yet, is she grabs from the center of the table task 4 and starts processing task 4. That was dynamic, right? It's because she finished first that she grabs the next task. Now, Bob is also done, so he grabs task number 5. And maybe now they finish task number 4. But what happens now is that since there is nothing left at the center of the table, they're done. So now Alice here is going to be waiting idly, right? Idly, yeah. Not sure if the pronunciation is good, but anyway. Now, Claudia here, I'm just making up names with ABC, is also done with task 1 and waits. And then Bob is also done. And now they are all done. In that case, I'm not going through any reduce phase because obviously the postcards are written, they just need to ship them now, but this is the idea, right, of what happens. So what did we learn here that we didn't see before? Is the idea that there are more tasks than people, right? This is very important. And in reality, you do want that. Because if you have exactly the same number of tasks as the number of people, then what's going to happen is that some people will be finished and then they wait in an idle way and you didn't use the fact that they were faster. But if you have, let's say, 3 times more tasks or 5 times more tasks than there are persons, then you see that the faster people, they are going to be able to process maybe 3, 4, 5, 7, or even 10 tasks. And the slower people will maybe process 1 or 2 tasks, but everybody just grabs the remaining tasks as soon as they are done, right? Who gets this dynamism, right? Okay, awesome. So this is the idea. And of course, it might not just be because a person is slow, it might be because the task is actually larger, right? It might be that for the specific inputs, it takes more time to process for a specific task. So that's the lesson learned here. We have more tasks than slots because these people actually, when we use machines, it's going to be the slots, the CPU cores. Typically 3 to 5 times more, but it's only a rule of thumb, right? It doesn't have to be exactly this. All right. Note that sometimes you cannot decide on the number of tasks because if you take it from HDFS, a task is going to be on a block of HDFS, right? Typically, you do 1 task corresponds to 1 block. But what you can control then is the number of slots, right? When you know the total number of blocks, you just make sure that the number of slots is a bit less than the number of blocks. Of course, it's not going to be faster, but it's going to cost you less money. So you're optimizing for the resources and the costs when you do that. All right. Okay, and now we are done. This is again called batch processing because they process the postcards in batches of 10. That's the idea, one of the ideas of batch processing. And you see, yeah, is there a question? Yes, go ahead.
So just that I understand correctly, we have less workers than actual tasks because we want to optimize for cost.
Yes, it's both optimizing for cost and time. It's dual to each other, right? You can either look at it from the perspective of optimizing on time by having smaller tasks so that you spread them more over people, and that way the faster ones will have more, the slower one will have less. But you can also take the other perspective that you're optimizing on cost if it's the number of tasks that you cannot pick and you can only pick the number of people, right? So either you have more tasks if you are blocked on a certain number of people, or you have less people if you are blocked on a certain number of tasks. Then either you're optimizing the time or you're optimizing the cost. But it's really more or less the same idea. Yeah? Go ahead.
Yeah.
I'll come back to you. Yeah. Yes, but only by having more tasks. So it's not like during the execution, you start splitting the task. It's ahead of the execution. Before the execution, you can just make the decision that you have twice as many tasks that are twice as small, right? But this is really ahead of the execution that you decide this, right? Go ahead.
Is the overhead of having more tasks negligible compared to the amount of work that we're doing with single task?
To some extent and up to a certain level. At some point, if you push that so much that now you have 1,000 tasks per slot, what's going to happen is you're going to have a latency problem. That's exactly, it's an opportunity to clarify what is meant with batch processing. Imagine that, it's oversimplified because this is an example, but imagine that we go to the extreme of having 50 splits, 50 tasks with each one postcard. Then first you would have to spread all of them over the table, takes more time to prepare. And then when people grab a new postcard, they have to reach from the center of the table. Or if you put it on a different table, they need to stand up, go get a postcard, and then come back to their table. If you have larger splits, larger tasks, they will stand up, get 10 postcards in a single go, and then come back. The number of times they will have to stand up will be lower. That's the idea of batch processing. Do you remember what I showed you in the first week of the lecture? The fact that the latency didn't improve that much, but the throughput improved more than latency. Having tasks that are not too small is one way of avoiding latency, right? Having these larger tasks is going to cost you less context switch if you consider it a context switch, right? So this is the idea. So it's really a balance between two extremes. If you have one single big task, it's not going to be parallelized at all. If you have one task for each key value, this is just going to be extremely costly in terms of latency. So the real optimal way to do it is in the middle of that, right? You need plenty of tasks, and the task must have plenty of key value pairs, right? And so as a rule of thumb, the size of an AGFS block is kind of a good sweet spot. Did this answer your question? Can't remember who asked the question now, I'm so confused. Yeah, that was you? Yeah, awesome. Did it answer your question? Awesome. Go ahead.
So in turn, I had to ask, like, what if we split the number of tasks into the exact same number of slots? Is that the optimal, or are there other better options?
So let's do it hypothetically. Imagine that you have one task for every person. So imagine we have 5 persons, and we have five tasks. Let me start with the ideal case where this works perfectly. It's the case that every one of these 5 persons writes with the same speed, and the quantity of words on a postcard is always the same. If this is the case, they will start the 5 tasks in parallel and finish at the same time. Now, this is great. This is optimal. The problem is that in reality, this is not what's going to happen. What's going to happen is that one person might finish very fast because she writes super fast. And then there's going to be one person, maybe because they have to write an entire letter to somebody who is going to take much more time. And this imbalance between the two is basically wasting the resources of all the persons who are finished earlier and are just waiting, doing nothing. So you're basically not utilizing the resources well. And by having more tasks, let's 3 times or 5 times as many tasks as people, you will nicely rearrange, if you consider like this a 2-dimensional triangle, where you have the time going like Y and the slots going like X. Then the area, you want to basically have as small a blank area as possible. The blank area is basically where people are idle. You want to minimize that blank area. And what you should visualize in your brain is that with 3 to 5 tasks per slot, you're going to be piling up the smaller tasks in the same slot while letting maybe a single task take the entire height of it. And the blank area is actually going to be smaller, right? And the reason why you have to visualize it 2-dimensionally with the time and the persons is how you are built when you use a data center like AWS. You are built per core or per machine per hour, right? So this is why you want to minimize the blank area, right? I think we can take a break. You deserve the break. And then I will continue in the second hour. It was very good to have the questions. Yeah, I'll come back after the break.